Binary search is a simple algorithm for locating an item in sorted list. The binary search in C program has few variation. Binary search in C is a simple process that can be used to solve complex problems. Through this course, we will learn what is binary search and binary search algorithm with the help of some examples and search demo along with binary search time and space complexity. We will also learn the implementation of different modes like iterative and recursive and a lot more about binary search with hands-on demo in C programming language. So stay right where you are and learn all that you can about binary search in C. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Now let's try to understand binary search algorithm. What is binary search? So binary search is one of the searching techniques, right? Like we saw in linear search, wherein the time complexity of linear search was big of n, right? We were iterating through all the elements, and now this is a much more efficient algorithm as compared to linear search. Now again, why do we need searching is the thing that, let's suppose if you have a given set of elements and you want to search if that element is present in your array or not, that time, right, we can use either linear search or binary search. Now binary search is much more efficient and it is used on a sorted array, or it can be used on an array wherein some order is maintained, because based on that order we will divide our array, right? It is a searching algorithm which follows the divide and conquer strategy, right? Let's suppose this is our array, and now since it will be divided in such a way that we can neglect one part of it, right? We will be dividing and then conquering. That means we will be then searching for our element. Now let's suppose we are looking for something that is, now let's take an example wherein this array is written, or the elements contained in this array are in such a way that if we skip this part, or the left hand side will be skipped or the right hand sides can be skipped in such a way that they don't affect our output. So every time in linear search, our search space is reduced unless and until we find that element or the array is exhausted. Okay, so our search space is reduced to half in every iteration. So this is what a binary search is. We'll look for an element in such a way that every time we are neglecting half portion of the array. And let's take an example when we have this entire array. So first half, that means if if there are 8 elements, 4 on this side, 4 on this side, these 4 will be neglected. Then we have 2 on this side, 2 on this side, these 2 will be neglected. Then 1 on this side, 1 on this side, then this one will be neglected unless and until we find that element or the entire array is exhausted, right? So this is how your binary search works. Now let's try to understand binary search algorithm. So first we are going to understand the iterative approach, and then we are going to understand the recursive approach. So iterative, as the name suggests, we are going to use for loops, right? We will start with a for loop and it will iterate, and we will iterate unless and until the beginning is less than the end, right? So because we will be updating our both beginning in some cases, and in some cases we'll update our end. Now what happens? Now since we know that in this iterative approach or in this binary search, it doesn't depend whether we are using iterative approach or recursive approach, the logic will remain same, right? So we will be having this array and it will be in some order so that we can neglect some part of it. It doesn't have to be sorted always. We can still apply binary search even if the array is not sorted, but still some order is there so that we can neglect some part of it. because again, keeping this thing in mind that it follows the paradigm of divide and conquer. So now we have this beginning and end at place, and we will always iterate when beginning is less than end, right? So now what happens after that? Now we have this array, and now what we will do, let me take new pointers. So this is your beginning and this is your end. So this is your beginning and this is your end. Now you will be taking a new middle index, right? M, let's call it M. And now let's name these things 0, 1, 2, 3, 4. So you will do what? Beginning plus end divided by 2, so that some part of it can be neglected, right? So it will be 2. So your mid is at this position. Now you will see, okay, the element that I'm looking for is, let's suppose, is 50, and the element that I am currently at is 30. So obviously it will be never from this side. There is no chance that we will be able to find 50 from this side, that is the left hand side, right? First we will check, okay, is this 30 equal to 50? No. So this will never be executed, right? Then we will check, is my item that is there, is this 30 less than or greater than 50? If it is greater than 50, right? If the element that is, if item that is 50 is greater than 30, right? Which is in this case, our 50, that is the element that we are looking for, the item is this point, is greater than 30. So there is no point that it will be on this side. So we will skip, or we will neglect this half portion of the array. So that is why our new beginning is updated. It will be new, it will be middle index plus 1, that is middle index was 2 plus 1, that is this will be our new beginning. So we have smartly skipped the half portion of the array. So now let's rub all of these things, and now let's see what happens in the next iteration. Now we'll keep this thing in mind, that we are not looping, or we are not exceeding this limit, that is beginning should be always less than, or it should be always less than or equal to end. Okay, so this condition should be maintained. And similarly we'll again divide our array and then look for the same things, right? First we'll look for the element, then we'll skip some part of it. So this is the iterative approach for binary search, right? Now let's look at the recursive approach or recursive algorithm for the same. So again, beginning, the ground rule will remain same. We'll always iterate, or we will always recursively call binary search unless and until this beginning is less than end. Done. Now what happens, we'll again find middle index, that is beginning plus end divided by 2. Then we will look for the element. These three steps will remain same even if you're using recursive approaches. Now what happens in recursion, right? We again call the function again and again. That is what is recursion. So in this entire tutorial we will be covering recursion as well, but in the later part of the course. Here you can get a good intuition, or let me give you a brief intuition about how recursion works. So let's suppose this is your activation record. Every time when a recursion is there, an activation record is called. So let's suppose you have these three statements. And let's suppose in your algorithm you have statement P1, P2 and P3, right? And at P2 you are calling the function again, right? You're calling this function again. So now what happens, an activation record is called. He will check, okay, is this statement executed? Yes. So one will be executed. Is second executed? Yes. So second is executed. But at second you're calling this function again. So at that time again a new activation record is created. Now this third step is left behind, right? Now this will be covered when we come back or return from this function call that we called here. So let's suppose this function was here. Now in here you are returning, right? This function called, let's suppose this is not less than beginning. Beginning is not less than end. So this will be somewhat, this case is relatable, right? This is similar to what we are looking for, right? Let's suppose there is some similar situation wherein beginning is not less than end. At that time you will be returning from this. Right now, once you have returned, you will be then calling this function again, but this time around for this. And let's suppose this time around you are calling this one is executed, step one is executed. Now again this activation record is called, this activation record is one, and then again this is called, right? This is executed again, this two is called again, a new activation record will be created, and these three steps, the step third will be still left for execution. So now here you return, right? Then it will go back to this step, right? And then once you are done with this, now there are two positions or two possible scenarios where you can return. Either you are returning from this function, just like we have executed this condition and we return, right? Another is that once you are done with this entire activation record, at that time you will also return. Okay, so these are two scenarios. Now you have executed this, there is no step to be executed, it will return. Now this was left behind, this will be executed. Now nothing is to be executed, it will go to the caller, which was this, and finally it will go to the main method wherein we call this at the first place, this function. Okay, so this is how an activation record is created, a stack is maintained. Okay, even if you might be thinking we are not using any extra space, but whenever recursion is there, an extra space that is in the form of stack, that stack is maintained. So you need to keep this thing in mind while you are playing around with space complexity at the time when you're using recursion. Okay, so now with that being said, let's clear our screen and let's see how recursion is called here. So again, now recursively what we will doing, if now we have this mid, right? And let's take an example of an array 0, 1, 2, 3 and 4, 10, 20, 30, 40 and 50. So middle index will be 0 plus 4 divided by 2, that is 2. So this is our middle index, right? So this is 0, this is our beginning and this is our end, right? So now we are hit here, right? So we again check the 50 that we are looking, this is our item that we are looking for. Okay, so is 50, and this is our middle index, is 30 greater than 50? No, it is not in this case, so this will never be executed. This is not executed as well, right? Now what about this condition, the else part? Now what we will be doing, we'll be skipping, since this 30 is less than, we'll be skipping this part and we will focus on middle index plus 1, which is nothing but this. So this will be our new beginning and our process will start moving, right? So now again then the same thing will happen unless and until this condition is false. Okay, so this is how your binary search works when you're using recursion. So now let's try to understand binary search and let's see its demonstration. Okay, so we are looking for 20 and this is our array, right? 10, 11, 16, 20 and 23. Now this array is sorted, right? So we can apply binary search. Okay, since we can neglect some part of the array based on some conditions. Okay, so now our beginning in the first iteration, what is happening, our beginning is 0, our end is 4 and our middle is this element. Now what we will be looking for, is 16 equal to 20? No, it is not, but 16 is less than 20, so we will skip this part. In the next iteration, what happens, we'll be focusing on these three elements, right? That is 20, we will be focusing on this part, rather, if we say we'll focus on this part, right? Focus on this part. Okay, so now in the second iteration, what will be happening, our beginning is updated. Now our new beginning is this point, our end will remain at its own position. Now we'll find the middle index, so it will be 4 plus 3, that is 3, that is 7, right? And divided by 2, it is 3.5, right? So since this will be truncated, right, the truncation will happen and the integer that is there, the middle index will be 3. So this is our middle index, right? So you can see middle index is 3. Now, is this an element that we're looking for? Yes. So we'll return the index. So we found our element at index 3 and hence we return 3. Because if you observe carefully, it is returning, if the element is found, it is returning the index. So this will be returned. Okay. So this is how binary search works. Now let's try to understand the implementation of binary search. First, we are going to see the iterative approach, right? We can see the iteration here. First, we see the iterative approach, and then we will see the recursive approach. This is the recursion, right? So now let's see first the iterative approach. As you can see, in binary search method, we have four arguments. One is the array, second is the item that we are looking for. Let's suppose it is 50, then the beginning index, that is 0, and the ending index, let's suppose it is 5. And the array that we have is of in the length of that array is 6. Okay, so this is the ending index. So let's suppose we have these elements 10, 20, 30, 40, uh, 50 and 60. Okay, done. So now we are returning, obviously, if there is no element, like let's suppose if we are looking for 70 and that is not present, so at that time we will return -1. So this return type will always be there, right? Because in either cases, right, if we don't have an element, we will return -1. If we have an element, we will return middle index. That will be the index of that element that we are looking for, that is the item. Okay, so in this case we are looking for 50, right? So beginning should be always less than or equal to end. That means we will not cross or will not see the situation where beginning is at or where beginning is greater than end. We'll see this case as well. Okay, so now let's try to do a dry run of the things that are there, that are here in this iterative approach. Okay, so now let's see. So first we will try to calculate the middle index. So what is middle index? How do you calculate it? It is beginning plus end minus beginning divided by 2. Now why we are doing this? Let's suppose the integer is of size 200, right? And earlier what we were doing and this is the size of the integer, and beginning is, let's suppose, 100 and end is 200. Okay, so now in this case, let's suppose this is the beginning plus end, that is 200. Now when we add this comes out to be 300. Then do we divide it by 200? But this then we divide it by 2, right? So this 300 makes this go out of the range. Now this is an overflow condition. Now to avoid this overflow condition, we will be using this. So it is 100 plus end, that is 200, minus 100, right? And then we have divided by 2. But this boils down to be only 200, which is still in the range of this 200. So you get the point, right? So this is for the same reason, to avoid overflow conditions. We use this beginning plus end minus beginning divided by 2. Done. Then we will look if the middle index. Now let's try to calculate the middle index here. Let me just erase these things. So first, what is the end index? In this case, it will be 5. And what is the starting index? It is 0. So 0 plus 5 comes out to be 2.5, which boils down, when we do the truncation, which boils down to 2. So the middle index is nothing but 2. So your middle index will be here. And this is your beginning and this is your end, right? Done. So now what happens when we are trying to search for the element, that is middle index element is equal to 50. No, it is not. 30 is not equal to 50. So now where we will go, we'll go in the second if block. This will not be executed. Then we are looking for, obviously now this 30 is less than 50. Obviously there is no chance that we will be able to find this 50 from this side. So we will reject or we neglect this part, right? And now our new beginning will be beginning is equal to middle index plus 1. That is, our beginning will be now here. So these are the 2 pointers that we take care of. The beginning, that is middle index plus 1, new beginning, and the end will remain same. So this is what happens since our middle index element was less than our item. So this will be executed and will not go into this, right? Again, now we'll check, is our beginning, right now our beginning is 3 is less than 5. Yes, it is. So again, we'll calculate what middle index, which will be 3 plus 5, that is 8, divided by 2, which is 4. Now this is our middle. So now I'm saying beginning plus end, but you actually what will happen, right? So our beginning is at 3. So this is 3 plus 5 minus 2 divided by 2. So it boils down to what? 5 minus 2, that is 3, divided by 2 plus 3. So what happens? This will come out to be what? This will be 1.5, something like that, and 0.5 will be truncated and you will get 1, and 3 plus 1 is 4. So your middle index is 4. Now this thing is done, and then the second step is that you will try to find out this thing, right? Let me just erase it, this thing. Our middle index is now 4. So you see in this block, what will happen? ARR of middle index, that is ARR of 4, is it equal to the item, which is 50? Yes, 50 is equal to 50. So now what you will be returning? The middle index, which is 4. So 4 will be returned and nothing will be executed from this point onwards. Done. This is the iterative approach. Now let's look at the recursive approach. So now for recursion, there is one thing that you need to keep in mind, right? What is that? So recursion internally uses stack, or it also uses activation record, right? So let's suppose these are, let's suppose you have three statements, right? P1, P2, and P3. This is the condition where you check the base condition. This is the recursive call, and then this is a print statement. So now when this activation record is created, 1, 2, 3 needs to be executed. But if this if block is not executed, right now we are not at the base condition, so this is done, right? The second thing is we are calling this recursive function again. So what will happen? Here we get the recursive call, and again the activation record will be created. So now this statement 3 is left behind. Again, what will happen? 1, 2, and 3 needs to be executed. So 1 will not be executed because we haven't reached the base condition. Then 2 will recursively call again, and this is left behind. So another activation record. So since it will be formed in terms of stack, right? So this will be the first activation record here, then the second activation record, then the third activation record, and one by one it will keep pushing it up in the stack. So now once we have reached the base condition, it will return. So this is the one return condition wherein you will reach the base condition, right? This is how you return. The second return is this. Now this will be popped out of the stack. Now what is the leftover statement? This is the leftover statement. Now this will be executed. Now once this is executed, that is the printf statement, whatever it is, it depends, right, upon what you're trying to do. So now this recursive, this third statement will be executed. Now this is how you return the second time. This is when your whole activation record is done, right? There is no statement which needs to be executed. At that time you will also return. So this is the second return, so you will return back. Now again it will be popped out of the stack, then it will be executed. This statement, the third statement, will be executed because the pointer which will reach at this point, right? Because this is done, this is done, this was the leftover statement, so this will be executed. So this is executed and it will return to the main function which it called. Now therein we have also main function at the beginning, right? That called the first function, right? So this activation will be recorded and main function will be popped out once we are done with this entire program. Okay, done. So this is a brief intro about how recursion works. We have a separate topic, recursion, wherein we will be talking about these base conditions, activation records, and all those things more in depth, and we'll also see some examples at that point. Okay, so we are taking one array. We have the item, that is 50. We have beginning index, we have ending index. Okay, done. And now we again check end should be greater than beginning. There should not be the case where beginning is greater than end. And then we find out the middle index, same as we did in the iterative approach. And then we check if array index is equal to the item. If yes, then we return the middle index. Else what we will do, if array index is greater than, then again recursively, here you see the recursion, recursively we are calling this binary search again, right, with revised arguments, that is array, item, beginning, but our middle index will change because the right hand side is not valid because the element is less than the item, right? So the middle element is greater than the item, so obviously it will not be from the greater side, so we are reducing from the end. So our end will be middle index minus 1. So we will have beginning and the middle index minus 1 will take care of the left hand part. Okay, so else if it is greater than, that means it will be on the right hand side, so we'll recursively call this will be called recursively. So at that time beginning will change, which will be middle index plus 1, end will remain as it is. If our whole array is exhausted and we're not able to find the element, at that time we will return minus 1. Done. Now let's see its implementation in code blocks. Okay, here you can see we are using code blocks and we have implemented it using C language. So we have this binary search method wherein we are implementing it iterative manner. So it is same what we have explained, right? What I explained you earlier. So we have the binary search, which takes in several arguments. We find out the middle index. We check if that middle index is equal to the item, the array of middle index, obviously. So then we check if it is greater than, or if it is less than, we do the stuff, right? Done. And in the main function, we have the static array, right? 13, 45, 65, 82, 117. It is sorted. Then we find out the length of the array with the help of size of operator. Then we need to see this item 82 that is there. We want this item to be found in this array. So obviously it is at index 0, 1, 2, 3. So 3 should be our answer. Then we call the binary search, and answer, whatever is returned, we kept it in the answer. So we check if answer is -1, that means element was not present, else we print the index. Okay, done. Let's build it and run it. Okay, so our answer should be 3. Index 3 is our answer, right? Now what about the recursive one? So you see binary search, and now here we are using recursion. You see, recursively we are calling binary search with the revised arguments. That is what happened. That is what happens in recursion, because we need to keep that function same for all the function calls, but with revised arguments. Only then we will reach this condition where end is greater than or equal to beginning. And when that is the case, that means we haven't found our element, and at that time we will return -1. That, so in that this thing is clear to you guys, right? And in the driver function, this time around we are looking for 117. So the index will be not 3 this time, index should be 4. Okay, now let's run this thing. Our answer should be 4. Yes, it is. So in this way, we saw both the implementation, that is using iteration as well as using recursion. Now let's talk about the time complexity of binary search. Now in the best case, now what is the best case? Now let's take an array, and in that array 1, 2, 3, 4 and 5. These are the elements. Now the best case is that, not that if the element, like we saw in linear search, this element, when we are looking to search for this same element, at that time that was the best case scenario for linear search, right? But in this binary search, the best case scenario is when your middle index is at this location, and you're searching 3 in the entire array. So at that time, this will take a constant amount of time, and this is the best case time complexity in that case. Okay, now in average case, what happens, right? If you talk about this algorithm, let me just clear out my screen. So it follows a paradigm of divide and conquer. So let's suppose you have 8 elements first in the array. It will be divided into 4, because these 4, or either it can be on the left side or on the right side, will be neglected. And then we focus on these things. Okay, these 4 elements. Again, it will be divided into 2 and 2. Then we will neglect 2 elements. Then 1 and 1. Then again, there will be one of the element can be neglected. So there are 1 and 1. So we focus on this element. So the entire operation will be done, or entire searching will be done in 3 steps, right? Now, I take an example, and if I do a log 8 to the base 2, what should be the value of this? Obviously, when I do this can be written as 2 raised power 3, right? And this can be written as 3 into log 2 to the base 2. Now this is 1, and now you get the answer as 3. So this 3 and this 3 are equal. That means if I talk about the worst case time complexity of binary search, it will be somewhere around log n. As we saw in 3 steps, we were able to find the element, and the log n, that means log 8, the answer of that is also 3. So you get the point, right? So the worst case time complexity of binary search is log n, and same goes for the average case, wherein it will be somewhere around log n divided by 2, neglecting log n divided by 2, neglecting the constant terms. It will be again, or it boils down to big O of log n. Okay, now let's talk about space complexity of binary search. Now when you talk about space complexity, right, we only think of auxiliary memories, or you can say that what any extra memory that you guys have used. Since we did not use any extra memory, that can be in the form of array, or it can be in the form of stack, or it can be in the form of queue, or linked list, or even strings, right? Since we never use these extra memories in our implementation, so the space complexity of binary search is bigger of one. That is, it takes a constant amount of space.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.